Today we're beginning what I would consider the second part of our study in calculus. We have studied all of the derivative rules that we're going to be applying. And so today we're going to talk about integral calculus, which is the inverse of what we have been doing, taking the derivative. So we're going to be given the derivative and go backwards to find the actual original function. That process is called antidifferentiation or the antiderivative. So here's a couple of examples. If this is my function, we all know how to take the derivative of that. We'd have 12x squared plus 2x, and the 5 would be a plus 0 out here on the end. So let me go ahead and take a look at another function. Here's we're going to take the derivative. We get 12x squared plus 2x plus 0 on this one as well, but we can tell that these two functions, f of x and g of x, are not the same function. They have a shift on them, up or down, and so whenever we are taking the antiderivative, because the constants on the end up being 0 in the derivative, when we take the antiderivative of those functions, we're going to have to add a plus c on the end of that. So if this is the now what I'm considering my function, and I want to take the antiderivative of that, then I would go back to what this was originally, here and here, but I would have to add a plus c on the end because I have no idea if it was a 5 or a 7 or a 10. We have no idea. And so we do add this plus c on the end to take into consideration the shift up or down. So the antiderivative is going to have some rules, kind of like we had rules for derivatives, so that we can go backwards, so we can figure out what the original function was. So let's look at this as an example. If I have the antiderivative of cosine, then my function prior to this, which we're going to call capital F of x, would have been sine, because the derivative of sine is cosine. But when I do this, I have to add a plus c, because if this is the derivative, then my original function could have had a shift on it that when we took the derivative just went away. So no matter what function we're going to anti-derive, we have to add this plus c on the end. So we're going to need to know our derivative rules, and we're going to work backwards from that. So at the top here is repeated what I just said. If these are my two functions, and I take the derivative of each of those, then we know that this constant went away. So if this is my function and I work backwards to figure out what it was originally, I have no idea what that was at the end, so I have to add that plus c. So we're going to try to think through some of these and see what we can do to figure out what the function would have been before. So if 0 is my derivative, what was it before that? Well, this would have just been a constant, because any constant that I take the derivative of, I get 0. So what gives me a derivative of 1? X. Whenever I take the derivative of x, I just get 1. Okay, so what gives me the derivative of x to the first power? Well, it would have had to have been x to the second power, but if I take the derivative of this, I get 2x to the first power. So not only is it x squared, but I also have to divide it by 2, so that when I take the derivative of this, so this is 1/2 x squared, I would get 1/2 times 2, or 1x. So it looks like whenever I put that square on there, I had to put it over 2 to account for when you take the derivative and bring that constant down. So let's look at x squared. Well, we know that's got to be x to the third. But the same thing happens here. If I take the derivative, I get 3x squared, and this doesn't have a 3 in front, so to get rid of that 3, I would have to divide by 3. So now when I take the derivative, it would be, bring down the 3 3/3 would be 1x squared. So with this one, it seems like we have a pattern going here. It's going to have to be x to the 4th, but in order to account for the 4, I would have to divide by 4. So what seems to be happening here is that whatever I have here, I'm adding 1 to my exponent, but then dividing by that same number. So what we've got here is going to be our basic power rule for antiderivatives. So down at the bottom, I'm going to skip this for just a second in the middle. Down at the bottom, it has our list, and this is the exact same things that we just went over in the chart. If I integrate, which is what this is called, antiderivative, or integrate 0, 0 would be a constant, because the derivative of a constant is 0. If I integrate 1 dx, then I get 1x. But it could have had a constant on the end, so plus c. This is the x to the n rule that we just did. If I integrate x to the n, I'm going to get x to the n plus 1 over n plus 1. If I have a constant, then that constant is going to get an x attached to it, plus c. And then if I have a constant in front of a function, I could always bring it out, because we all know that the constant is just kind of a tag along. Or I could separate my function. So this little symbol here that I just kind of threw in, that's called the integration symbol. So this is the integral. It means to take the integral. The function itself that's inside there is called the integrand. This is the variable of integration. You know, we take the derivative with respect to x normally. So this is what our variable of integration would be. And then this is just the constant whenever we find our antiderivative that we add on the end to account for our up and down shift. So the integral of f of x dx equals f of x plus c. So the integral is the same as the antiderivative. Integral, antiderivative. They mean the same thing. So with what we did up here in our chart, and with our list of basic integration rules down here, we're going to try to do a few of these problems. Now, since our basic integration rules are similar to our power rule for derivatives, then what we need to do for most of these is rewrite them with our exponents. And then we can use our rules. So remember that whenever we have this in the denominator, to bring it back up to the top, we make it negative. And then if I want to use these rules over here, it is now like this. So I just add 1 and put it over the number plus c. So if I add 1 to negative 2, I get negative 1. So this is going to equal x to the negative 1 over negative 1 plus c. Or the x comes to the bottom, we get negative 1 over x plus c. All right, let's try the next one. We need to rewrite this so that we have exponents. So we're going to have the integral of x to the 1/2 power plus 1/2 x to the negative 1/2 power dx. So x, the square root is the 1/2 power. This is my 1/2 that I put in the front, and this is in the denominator, so I've got to bring it back up, so x to the negative 1/2. So now when I integrate that, I just use the rule for adding to the exponent. So if I add 1, 1/2 plus 1 would be 3/2. So I'm going to get x to the 3/2 over 3/2 plus 1/2 times, so now I'm using this. I have a constant, or a constant times my function. So I can just tag that 1/2 along, 1/2 times, and then this is going to be add 1, we get x to the 1/2 over 1/2 plus c. All right, so we're going to flip this thing over. When you have when you divide by a fraction, you flip and multiply. So this is really just going to be 2/3 x to the 3/2 plus, and then this would be times 2 over 1. So this is 2 over 1 times 1 over 2. Well, that's just going to go away. And then we have x to the 1/2 plus c. All right. When we look at this next one, we're going to need to rewrite it first. Now, since none of the rules that we went over had to do with quotient rule, we haven't talked about that, then we do need to split this thing up. So we're going to have the integral of x to the 1/2 over x squared plus 1 over x squared. I just split it up this way, and the square root is the 1/2 power. So let's go ahead and kind of simplify this out. Oh, that does not say 1/2. All right, so whenever you're dividing, you subtract the exponent. So 1/2 minus 2 would be -3/2. So I have x to the -3/2 power plus x to the -2 power, because we're going to bring that back up, dx. So now we're ready to use our rules again. So we're going to add 1. That would give me -1/2. -3/2 plus 1, or 2/2, would give me -1/2 over -1/2 plus, and then add 1, I'd have -1, x to the -1 over -1 plus c. Well, again, we're going to flip this over. So flip it over and I get -2. So I have -2, and the x to the -1/2 would go to the bottom and become x to the 1/2. Then my -1 can be on the top or the bottom, so I guess really I should just put a minus in here. It is going to be negative or minus 1 over x. The negative exponent moves to the bottom, plus c. All right, so number 6 here. Again, in order to use the rules that we currently have, we can only use the power rule. That's the only rule we have for our integration. So we're going to need to multiply this out so that we can integrate it. So when I have 3x plus 5 times 3x plus 5, I get 9x squared plus 30x plus 25. And then I can integrate each one of these. So the integral of 9x squared, constant just tags along. I'm going to get 9x to the 3rd over 3 plus 30x to the 2nd over 2 plus 25x plus c. Well, this will reduce 9 over 3, so we get 3x to the 3rd plus 30 over 2 is 15x squared plus 25x plus c. There we go, sorry. All right, our last example. So this one's actually fairly straightforward. We don't have to manipulate it at all before we begin. So we're just going to use the power rule on each portion of this. So 5 tags along. We have 5x to the 5th over 5 minus 8x to the 4th over 4 plus 9x to the 3rd over 3 minus 2x to the 2nd over 2 plus 7x plus c. So this reduces. We have x to the 5th minus, these reduce to 2x to the 4th plus these will reduce to 3x to the 3rd minus these reduce to 1x squared plus 7x plus c. So we're going to add to this our basic integration rules for our trig functions, and these are just the reverse of our derivative rules. So we're not coming up with some new rules for just the secant or just the tangent. They have to fit into these categories for us to be able to take the antiderivative at this point. So the antiderivative of cosine would be sine, because the derivative of sine is cosine. The antiderivative of sine would be negative cosine. That's because the derivative of cosine is negative sine. So in order to take care of that negative, we would have to make the antiderivative negative cosine. Also, remember the derivative of tangent is secant squared. So if I integrate secant squared, I'm going to get tangent. Same here, derivative of secant is secant tangent. So antiderivative of secant tangent would be secant. The derivative of cotangent is negative cosecant squared. So if I just have positive cosecant squared, the antiderivative would be negative cotangent. And the derivative of cosecant is negative cosecant cotangent. So if I antiderive cosecant cotangent, I'm going to get negative cosecant. That takes care of our negative sign. So let's try a few of these trig applications. All right, so we're going to go ahead and distribute and see what we have here. We have the integral of secant y tangent y minus secant squared y with respect to y. So secant tangent is right up here. It's going to give us secant. So the integral of secant tangent is going to be secant y, and secant squared right here would be tangent. So if you know your derivative rules really well, then this is going to be pretty easy. Now, if you don't know your derivative rules for your trig functions, then this is going to be kind of hard, because now we're working them backwards. All right, the last thing that we're going to do here is talk about that plus c. So if we know that plus c takes our graph up and down, if they give us a specific point on our graph, then we can probably find that plus c. So let's look at this equation. They want us to take the derivative, or look for the curve. The derivative is x squared. They want to know what was it prior to that. And we know it's going to be a cube function graph, so one of these graphs. So let's go ahead and integrate it. Remember, this is probably a good time to point this out. Remember how we had this dx on the end of our integrals for all of these problems? We always have this dx out here. This is y. Whenever we have our derivative, this is one of the ways we write the derivative dy dx. If I were to multiply both sides by dx, then I would have the integral of dy equals the integral of x squared dx. Well, the integral of 1 dy is just y. So that does take us back to the original function. So the dx has to be on the side where it's with respect to x. So on this side, when I integrate, I'm going to get x to the third, and we have to put it over 3 plus c. So now they've given us our point 3, 8, so we can plug that in for x and y and see what c is. So 8 equals 3 to the third over 3 plus c. 8 equals 27 over 3 plus c. So that's 9. So subtract the 9. C is negative 1. So our equation is y equals x to the third over 3 minus 1. So if they give us some specifics, then we can find our c. This is called finding the particular solution for that problem. The plus c, lots of solutions. But if we have a point, we can find the particular solution that goes with that problem. All right, so they have one more example for us here. This time it's a second derivative. So this is our second derivative. They want us to find the original function, which means we're going to have to go backwards twice. All right, so we're going to integrate 12x squared plus 6x minus 4 with respect to x. So that's going to give me 12x to the third over 3 plus 6x to the second over 2 minus 4x plus c. Or that would be, let's see, 4x to the third plus 3x squared minus 4x plus c. Okay. Well, they didn't tell me anything about that this function is our first derivative, right? We've gone back once, so this is going to be equivalent to f prime. But they didn't give me any particular information about f prime, so I'm going to have to just use this and go back one more time. So now we're going to integrate 4x cubed plus 3x squared minus 4x plus c. So this is going to be 4x to the fourth over 4 plus 3x to the third over 3 minus 4x squared over 2 plus c with an x, because that's a constant. So now if I were to take the derivative of this, I would just get c. And then we have another constant. So you could call it whatever you want. I'm going to call it d. So this is what we have. This is our answer. Now this will simplify a little bit. So we've got f of x equals x to the fourth plus x to the third minus 2x squared plus cx plus d. But now they've got some particular information here. So I'm going to start with this f of 0 equals 4, because if I know f of 0 and I plug in 0 for all of these, this is 0, 0, 0, 0. So f of 0 is going to be d, and d is 4. So now I know that much. I'm going to plug that in, and I've got f of x equals x to the fourth plus x to the third minus 2x squared plus cx plus 4. Now I'm going to take this other piece of information here and find f of 1. So let's plug in 1. So I can slide this up a little bit. We're going to plug in 1 now. F of 1 will be 1 to the fourth plus 3 times 1, which is 3, minus 2 times 1, 1 squared, plus c, because x is 1, plus 4. And I know that this is supposed to equal 1. So I get 1 plus 3 is 4, minus 2 is 2, plus 4 is 6. So 6 plus c equals 1. Let's see here. And so we get c is negative 5. Let's make sure we got all that right. Oh my goodness, mistake here. We have x to the third, and I wrote 3x to the third. Alright, so if I take that 3 away, that 3 would make this a 1. What does that now add up to be? That'd be 2 minus 2 is 0 plus 4. So 4 plus c is 1. C is now negative 3. Negative 3. So negative 5. Alright. So we have our function now. F of x equals x to the fourth plus x to the third minus 2x squared minus 3x plus 4. Alright, so if they give us this particular information for the particular solution, we can go back and find our c value. So what we have here are, our trig rules, which are just the derivative rules backwards. And we have over here our basic integration rules, which really, we have this power rule, and we know that, 0 is always going to end up with a plus c. The derivative of 1 is going to be an x, or the derivative of a constant would be the constant times x. And we can take each part individually and find the antiderivative or the integral.